receive
Recording in
horizontal
progress.
or the other way around. This has some differences and some uses, and I will come to that in a couple of slides in a bit more detail, where we talk about a little bit about the differences of those. I also want to make clear, technically speaking, just from pure technically, we would not be limited to only vertical and horizontal, right? We could design filters in all different angles. That would not be a real problem, right? Technically speaking, it is more as humans, we very much like such things like a vertical filter. Horizontal, we don't really like something like 45-degree. So it's more a thing of our rather stupid human brains, right, who really like vertical and horizontal things. So there is not really a limit, and there's also talk on applications with 45-degree polarizations and so on. Nevertheless, typically until now, most of the SAR sensors, they're limited to vertical and horizontal. And when we have all four of them, the VV, the HH, VH, and HV, then we can reconstruct a complete polarization matrix anyway. And I will talk a little bit about that in a couple of slides. However, the field in general, the field of polarization, is also a very huge field, okay, which would really be also interesting to have a complete lecture about that field alone, right? I would also recommend that. It's a very interesting topic, also a little bit complicated topic, but I'm not really covering that here. Just in a few slides, I show a little bit about it. All right. Can we define resolution of SAR data in terms of spatial units? What actually resolution mean in SAR remote sensing? So I showed you the slide of the resolution of a SAR system here. And that is given, in meters. Okay, this one would be given in meters, right? However, in the range direction, that would be the direction, the meters in this slant range image. I will also talk in a few slides again a bit about that, because these resolutions here on that slide, they are given in meters, but what we actually measure and what's the unit of measurement in our SAR image is typically a unit of time, actually. Okay, and that's a good question, right? Can you explain again why SAR sensors are side-looking? And this is a very important question, because that's an important point, and I think I did not make that clear enough on Friday. So first of all, you have to understand that let me turn on the video a bit. Okay. You got to understand that you have a very large beam, right? So that means you don't have like a small laser, right, with a very small beam. You have a really huge, the signal that's going out is really out in a very wide beam. So, for example, when we have here the antenna with an antenna size of a typical antenna size of 10 meters, you will end up at a given range with here with something like easily 5-kilometer beam. If we think about the ERS system, right, it has a footprint on the ground, and that is about 70 square kilometer footprint, right? So the signal is covering 70 square kilometers. So you have a very wide beam coming out of your antenna, right? So to get a very narrow beam, you would need here a 5 kilometer long antenna to get something like a 10 meter beam that has a 10 meter footprint on the ground then. So what we are dealing with is really a very wide beam, okay? So that's what you need to understand. It's very different from other sensors. So if we now have such a very wide beam like here on the left side, right, then, and you would put that looking toward the ground, looking downward, you will cover here a large area with one pulse, with one beam, okay? So the left side here of your signal and the right side of your signal, they are at the same distance, okay? They will come back at the same time. You could not separate at the end the left part of your image from the right part of your image. You had no way to separate those. The signal would be returned at the same time. You don't know from which side it's coming. So you would get an ambiguous signal, and that would be basically useless. Okay, if you have you don't know is it the left side or the right side of your image, you can't separate them. It's not gonna be a good system. Okay. However, if you look to the side, then you can separate the objects in the range direction just by looking at the time again, right? So if you're side looking, then you can separate where is the pixel coming from by looking at the running time, even if your beam is very, very large. It doesn't matter in that case. When you're looking down, you cannot separate the left side from the right side because you have such a huge beam, right? It is not anything like a laser system, for example, where you would have a rather small footprint and you would scan along. It's not like that. It is one pulse that we then, in the synthetic antenna, we combine them together to get a higher resolution, but we cannot separate, even with the synthetic antenna, we cannot separate ambiguous signals. This is just something we can't do. So we have to have a side-looking system, right? That causes many problems in terms of geometry, and I will talk about that again, but there is no technical way around it. Okay, so that has been the questions from last time. Keep on asking questions. I will try to answer them personally. I agree also with Sishan. And I think it's the most important part of this course. As he said, otherwise, you could just watch videos, right? Or get even better made videos on YouTube. Okay, then what we're doing here, it is generally in a lecture, it's the interaction that makes it really worth it. We have now at the moment like more than 300 people joining us, which is great, but we can't have a good interaction with 300 people. But you can ask the questions and we use the time to answer the questions. Okay, so use that. It's very, very useful. Also for me, for example, I just learned, right? I mentioned that you have a side-looking system, but I maybe did not explain it clear enough. Okay, so if I get the questions, I have to think by myself, okay, yeah, maybe I need to explain that a little bit more clear so that people understand it better. So it also helps me, okay, to see where you don't understand it so well, where I maybe need to explain more. If we would sit together in a classroom, okay, if we are in a classroom, I can see in your faces, okay, I can see in your faces sometimes, you know, if I speak too fast, too slow, if you did understand it or not. But here I don't have this option, okay, but you can use the questions to help me and help yourself. Okay, enough of that. Let's continue a bit for today. We're continuing with the geometry. I showed that Friday last time a bit with the foreshortening effect. But let's go that again in another slide and try to understand you. Now, let me see that annotation here again. Okay, right. All right, okay. So I hope you can see that. Let me check it out. So this direction here, okay, this is what we call the slant range. Okay, that goes down here. Okay, slant because, well, it's not ground range, it's slant in the direction. Oops, that was not nice painting. Slant in the direction of the signal. Okay, that's we could say that's the original axis of the SAR image, right? This below here, that would be the ground range. That would be the position on ground. You could say that's the real position. So if we take a look here and we send our signal, okay, and the reflection here of this point A, okay, that would be on the slant range here where we have the A dash here, okay, and B, because it's a little bit closer to the signal, to the sensor, you see that range here, right, this dotted line, that is the dotted line, the dotted line here, that is the line of the same range, okay, the ISO range line, if you want. So if we go from point B to B dash, right, that would be on the SAR image, that would be mapped here. And you see the distance from A dash to B dash is much shorter than the actual distance from A to B on the ground, okay? And this effect is called foreshortening. So if you think the hill, the mountainside, the side of the mountain that is toward the sensor, that side is shortened. It will be shorter in the SAR image than it is in reality. While the other side, you see the distance from B dash to C dash, right? This distance here is longer than it would be on the ground, right? A, B, C, they're actually the same distance. A to B and B to C is the same distance on the ground. So you see, this is the range distortion, because what we are measuring is the running time of the signal. The running time of the signal is then, if you want, translated to distance. So we have a distance measurement, right? And B is just closer to the sensor, right? Because it's higher. So it is then closer to the signal than it's actually on its ground position where it should be. Now, that's if we have something like mountains. Now, if we have a more steep mountain or buildings, right, it's getting even worse if you want. So if we look, let's start with point D down here at the building foot. Okay, so he's positioned right at the correct position, the dash here, right? Now, E, that point here, on top of the building, he's closer to the sensor. So E dash will be in the SAR image before D dash, right? So the point is even before, and even point F, which is, if we look on the ground, is behind the D, is also imaged before D in the SAR image. And this effect is called layover. That's the so-called layover effect. So E is then before D. And this effect has even one more problem, right? That this point on the ground, the small E, okay, the small E, that is the point on the ground that has the same distance like E to the sensor. And the signals from this point on the ground and this point here on the building, they will also be returned at the same time, right? Which is to say, you can't, at the end, you can't separate them, okay? So at the end, you wouldn't really know did I receive now something from the building from this capital E or from the small e on the ground? They come back. These two signals will come back at the same time. You have an ambiguous signal then, and this is the so-called layover effect. Okay. Now, the last point G, or the points, the area behind that here, that would be the shadow area. Okay, so this area we can't really see. Okay, it's the area we couldn't see. This is the radar shadow. I think actually the radar shadow is relatively easy to understand, right? Because, well, it's in the shadow of the radar signal. We cannot see it. I think that makes sense to everybody. Well, layover and foreshortening, it's not so easy to understand. Okay, actually, it takes some time to look at SAR image to really understand a bit what that means. I can show you many slides. Okay, you're gonna need some practice to see it, but I hope this slide here can help you a bit more than the slide I showed before. Okay, right. Okay, let me. Okay, all right. Now we see that a bit here with an example with an ascending and descending image. Now, on Friday I mentioned that. I mentioned that we have orbits, the ascending orbit and the descending orbit. If you remember that, our satellite is going around the Earth. The Earth is turning right under the satellite, right? And one time the satellite comes up, ascending, and then he goes down, descending, ascending, descending, ascending, descending. And so each point on the Earth, because the Earth is rotating, can be seen from ascending direction and then another time from descending direction. So you have then one time, we see that is a more basically an east to west direction, not exactly, there's a little bit, there's 10-degree difference, and a west to east direction. So the image here below is right, that is ascending, right? It's an ascending image. And you see here, let's take a look here on these high-rise buildings. Right, I make that one on again. Okay, so let's take a look. See, these are some high-rise buildings here, some skyscrapers here in Wuhan. Right, this is the layover here of a building. So the building, the original building is positioned somewhere here. Okay, but it's in the SAR image, it is mapped in this layover direction here. So the top of the building is closer toward the sensor direction, right? So you look in this direction and the layover goes in this direction toward the sensor. Okay, so you see that these high-rise buildings, they all then move toward the sensor here. And if we look from the other direction, here from the descending direction, they go again toward the sensor, but it's on the ground, it's a different direction, right? It's almost the opposite direction. Okay, now that is the layover effect, but this effect makes it very difficult for you to interpret and understand the SAR images, right? If you have a dense urban area, like here with lots of high-rise buildings, it's difficult to understand it. We see the buildings, right? And we can understand that is a high-rise building here. Okay. But for example, we don't see anything that is here in front of the building because of the layover. And even more, if we compare images from different directions, from different angles, it's very difficult to compare them, right? It's difficult to compare this image here with this image here, right? They look very different because the layover effect goes in a different direction. Your buildings now, the shadows are in a different direction. Your buildings and the whole situation on the ground is very different, right? To interpret that and analyze that is then difficult. And if you imagine, let's say you work on change detection, right? You want to detect damaged buildings after an earthquake. It's going to be very difficult, right? If you compare an ascending image with a descending image, right? It's going to be very difficult to identify the changes in the buildings, missing buildings, damaged buildings from very different looking angles. And if you think about and you would go with any, let's say, any pixel-based method where you just compare pixel by pixel, it's pretty obvious that none of them would actually work very well, right? So I hope that helps a bit understand A, the effect, and B, the problems that this effect brings to you. You can't really compare them easily. Okay. Yes, I like meeting them at the same time. Okay. All right. Now, another of these slides where honestly I never know where to put them. Okay, they just come out of nowhere. Okay, I don't know, but I still believe it's a very important slide because it gives you a little bit what is in a SAR image and the different names on that. So let's take a look at that slide here in some detail. So we have two directions of our SAR image, right? We call it the range direction and the azimuth direction. Now, I think nowadays, in most cases, right, the range is in X direction and azimuth is in Y direction. However, that is not clearly defined. Okay, images can be different ways, and there are also some providers and some software and tools, they do it differently. Okay, they change azimuth and range. Then azimuth is in X and range is in Y direction. It's not defined. You need to know which one is which, right? There's also a different name for range. Range is sometimes called fast time, and azimuth is sometimes called slow time. Why? Because in range direction, as well as in azimuth direction, the unit of from one pixel to another is actually given in time. So in range direction, that is here given basically with the speed of light, right? They give you the time difference from one pixel to another is a time difference, very small time difference because it's the speed of light difference between these pixels in range. There can be a very small time then difference. And in azimuth, it's also a time. It is basically the flying here. It is much slower because it's the flying time, the speed of the satellite by the pulse repetition frequency. How often you repeats the pulses. This can then be transformed into meters. Okay, so but typically in the so-called slant range image, in the single look complex image, they are given to you. The format gives you that in timing. Now it is important for you to know these words a bit. Okay, that you have a range direction, azimuth direction, and there's sometimes some papers, maybe people write it is fast time and slow time. You don't see these two words very often, but you see them sometimes. Then you have the SLC image, the single look complex image. That is one image type that you can order. Okay, if you get a SAR image, sometimes you get a whole bunch of different types that you can download or order, right? And you may have the raw image, which would be, I showed you a raw image on Friday, which you still need to focus. That's normally not what you want. You may get an already geocoded image, right, which you then directly can use. Is already geocoded for some application that might be what you want. And then we have the single look complex image, which is basically the first processing level after the raw image, the directly focused image. This is what you want if you want to do interferometry. We're going to later talk a lot about interferometry and INSAR and all these processes. And for all of them, you want the SLC image, single look complex image. That's what you need to do that, right? The single look complex gives you, well, a complex number, okay? A number with a real and an imaginary component that you then can also transform into amplitude or a phase, right? So that is then what we need to process interferometry. And then I have here, in other words, pixel or resolution cell, right? So in SAR, we use these two terms. One is pixel and one is resolution cell. Sometimes we use them synonymously, okay? The best definition of the difference that I know and I try to use is that we say in the SAR image, okay, this is a pixel, okay? And the resolution cell describes the area represented by that pixel on the ground, okay? So that is the definition, but clearly we sometimes use them synonymously, a complicated word, right? And interchange them and sometimes, but just so that you know the words pixel and sometimes resolution cell. Okay, so these are terms that you can look up. And as Sishan said, we will give you the slides soon, right? Not sure, maybe the best is in the course. I'm not sure on how, but you're definitely gonna get the slides, okay? That's not gonna be a problem. Then you can look that up again. Okay, so I have to close that to move on. All right, so let's talk a bit about the radiometry. We talked a bit about the geometry. Let's talk a bit radiometry. So why is a pixel white and why is another pixel black? This is basically what we discuss here. So we have the terrain effect. So because we have a side-looking system, all right, so if our system hits such a site here, right, such a mountain site here, right, this is then almost here, you see this is almost like in a mirror direction. Okay, it's almost, right, like a mirror. So you get a kind of a strong reflectance from that. Okay, you see something like that gives you a strong reflection. Behind that, you don't get a signal. This is a shadow, right? So you get no reflection here, right? And then more kind of a normal reflection strength here. Actually, there's another reason why this area here gives you quite a strong reflection. There are two reasons behind that. Number one is, as I mentioned, this is like the angle is very close, so you see a larger area here. It's more like a mirror direction going back. That's one reason. The other reason is the foreshortening effect that I mentioned before. You see this one, this area here is shorter, right? It is shortened down. So, and at the same time, the whole energy is the same, but it is shortened from the foreshortening effect to a smaller area. So per pixel, you get more energy. Therefore, your pixel is going to be more bright. Okay, normally the area is so long, it's foreshortened to here. Per pixel, now you have more energy. But it's also additionally the angle. If you, well, let me see that you see that, right? If you hit that from this direction, you get less reflection. You see a smaller area than if you hit it from this direction. Then you always have like a mirror, and also the area that you see from the surface is larger. Therefore, that side of the mountain is more white in the SAR image, and the back side is more dark. Okay, that's one of the terrain effects. Okay, this slide I already showed, but I can't show it often enough. It's the basic reflection. So we have the diffuse reflector on A here, the diffuse reflector. That means you signal hits a rather rough ground in a perfectly rough ground. The signal will be reflected in all directions with the same strength. Okay, it's going to perfectly reflect in all directions. The whole energy is then going, you can say, divided, right, into all directions. So only a very small fraction of the energy is coming back to the sensor, but something is going to come back. While if you have a specular reflection, right, a lot of the energy is reflected away in one direction, but that direction is away from your sensor, and you get nothing back. So that pixel would be very black. Okay, it's a black pixel. You don't get any energy back. And the last standard reflection method is the corner reflector. You hit a specular surface, or also a diffuse surface in front of it, but let's say a specular surface. All of the energy is reflected away. It hits then this wall of the building, another specular reflector. But then, due to the geometry, this one is reflecting back to the sensor, and you will get a very strong signal back, much more stronger than what you get back from the diffuse reflector. So this would be a very, very white, a very bright pixel at the end. It's a very strong reflection, and it's very common. It looks like a strange occurrence, but actually corner reflectors are very, very common in urban areas and many other things. Everywhere where you have basically perpendicular surfaces. And again, humans really love to build perpendicular surfaces. So whenever you have man-made objects, you have a lot of corner reflectors typically. So that's why we see cities so good in radar image. They will be very bright because we have lots of corner reflectors there, and they reflect very good. The roughness of the ground, you see, is we just now described only two, right? Very rough and smooth, diffuse, and specular reflection. But it is a continuum, right? It's a continuum between smooth and rough with intermediate roughness levels. And it also clearly depends on the wavelengths of your system. So if you have a very short wavelengths like X-band on the left side, then something is becoming rough with respect to the wavelengths. Is much more sooner than when you have a 20 centimeter L-band wavelength. So the smoothness and roughness of the surface is to be seen in relation to the wavelengths, right? And in relation to 3 centimeter wavelengths or an L-band and 20 centimeter wavelengths, that is also something very different than the roughness in an optical sense. right? We have a very different wavelengths to deal with. So things that are, clearly rough in an optical sense, they can be very smooth for an X-band system, and even more so for an L-band system. And that means then something like, for example, a road is typically very smooth with respect to a 3 centimeter radar. Right? There is not much changes. There's not much jumps in it. If you think about a 3 centimeter wavelength, that such a surface is very smooth, and therefore that would reflect like a specular reflection, leading then to, let me go here. Like if you have a road in front of the building or parking space or something like that, right, that would then lead to very easy to specular reflections. And so you get these corner reflections really very, very common. Okay, the roughness of the ground is here, one of the criteria. Then we have volume scattering. Volume scattering is your signal is your SAR signal is penetrating the material. Okay, for example, if you have a forest canopy, the signal is going, it's going in that canopy, it's going inside, and then inside that canopy, okay, so if we go here inside, okay, then we are, you see some is reflected on the top, maybe some goes a bit down, is reflected here again from another bigger twig or from some leaves, okay, and some go in and they get reflected again inside multiple times until some of the signal comes back. Okay, so it's a very chaotic reflection regime. You get lots of reflections inside the volume, and some of that comes then back. Now, this can be a forest canopy. If you have longer wavelengths, it can also be a very dry sand. Okay, it can be ice. There are some elements where the radar signal can penetrate. However, just because this question often comes, it's not going to penetrate very deep. Okay, it is at all as soon as you hit, for example, groundwater or a moisture layer. Okay, you're already gonna get reflected. So we talk about you can penetrate very, very dry sand, so some soil which is not so compact and is very dry. So something like in a sand desert, you may see that with long wavelengths you can penetrate a little bit deeper, but on typical ground you're gonna stay with the soil on a couple of centimeters. Okay, you're not really gonna get down and really see underground or detect any. You will not be able to find gold, okay, underground. Just to make that very clear, in terms of soil, you're gonna stay very near the top. If you have a very long wavelengths and very dry sand, you may get some deep, a couple of meters. Okay, but this is like the exception. Okay, now what you enter with longer wavelengths is something like forest canopy. You're gonna actually get a signal. If you have long wavelengths, the signal is gonna through the whole forest and reach the ground of it. And also you can go rather deep in ice. If you have an ice fixture, you can go relatively deep in that. Okay, that is the volume scattering. Moisture plays a big role. I just mentioned that. So if there's the SAR, the radar is reacting to the electrical materials that are conducting energy, like power. Right. If you have a conducting surface, you will have a reflection there. And water is a very good conductor, right? So if you hit water, you're gonna see a reaction. So moisture will reflect stronger if you have higher moisture in your soil. You have a higher dielectrical constant and you get a higher radar return. So radar is able to detect soil moisture, right? We can use SAR images for soil moisture. We also use commonly then passive microwave systems for soil moisture things, to detect soil moisture and work on that. So there is a strong relation between the water content and your radar return on the ground, or the water content also inside vegetation. It is typically when we are in the nature, when we are talking about nature scenes, it is typically the water, or the water inside the soil, or the water inside the plant that is actually reacting with your signal, right? So the moisture is very, very important, and that can be very good if you're interested in soil moisture, right? But it can also be difficult if you are not really interested in soil moisture, right? If you want to classify other things, yeah? If you're interested in classification of the crop types, for example, and then you see that the moisture of the soil is changing your reflection. That's to say, has it currently rained or not, gonna change your radar signal probably more than what type of vegetation you have here. So you have to be aware of that there is lots of influencing factors on your radar signal that you maybe do not want, okay, to influence it. Depends on your application, okay? If you're interested in soil moisture, great, but often we are not. So soil moisture in general plays a very big role in the radar reflection. And I will show you another slide later to show that again, right? Side lobes, so if you have a very strong echo, if you get a very strong reflection from, I don't know, you have something which reflects very strongly, okay? Now this reflection can be so strong that because of the also kind of the imperfection of how we collect the data, we can get these side lobes, right? And so you have that strong echo, and then you may find such lobes on the side. And I show you some examples also later of those. They can be very disturbing, actually, right? We do not like them because actually they are not something that we are interested in. Okay, we're interested in the strong signal, yes, but the lobes on the side, they are then a different position and something we do not really want. And they can be very prominent in a SAR image. Right, another form of those are ghosts. There are many. Ghosts is typically a signal that we do not want, sometimes a signal that we cannot explain in a SAR image. Also, we have them here at the side of the footprint, right? At the edge of the footprint, we sometimes see such ghost signals appear. Them, I will show you in a slide what that means. That can also be, again, very, very annoying. Okay, and sometimes we use that term ghost also sometimes for other signals which you just cannot explain. And unfortunately, in SAR remote sensing, there are several of ghosts and signals that we cannot really always explain, right? Okay, so one is that at the edge of the footprint. I show you an example of that soon. All right, Speckle, I already mentioned that, but we can't talk often enough about that. Speckle is something that, yeah, makes our SAR images so ugly. Okay, if you want, there's kind of a noise-like effect on it. It comes from the random positive and negative interferences of the waves from these different scatterers inside one pixel, inside one resolution cell. So if you have many small scatterers in one resolution cell, they reflect and then they interfere each other with positively or negatively, right? So that leads to some varying brightness, and it leads to this speckle effect, this noise on top of the image. It's not actually a noise because it is a signal, right? But it, in most cases, we can say it acts like a noise. Okay. We will talk about it a lot. Important at this second, A, it's noise and we do not like it. Okay, it's ugly. But B, remember, speckle means it comes from, right, let me focus that part here. Again, I have to click several times, doesn't matter. From the many individual scatterers. Okay, many scatterers in one pixel. That's to say, if we only have one scatterer in a pixel, we do not have speckle. Speckle comes from many pixels, many small scatterers in one resolution cell. If we have that, then we have speckle. If we would only have one, we do not have speckle. Okay, we may have other forms of noises, but it's not going to be speckle, and that's going to be important later on, because later on we will differentiate, we will separate pixels who suffer from speckle from pixels who do not suffer from speckle, and that's by defining there is only one strong scatterer in this pixel, then it doesn't have scatter, then it doesn't have speckle, right? And then we have one less random problem to worry about. What we do not like about speckle is that it's act randomly. It's not really randomly, because if you would take the same if there's all the scatterers stay at the same position, and you take 2 times the same image, and everybody stays at the same position, you will get the same effect. Okay, the speckle will look the same. So it's not really noise. But you can't do that. Everything is changing all the time, and you never come back at the same position. So you have speckle, and it acts like noise. Okay. And okay, speckle statistics. So how we deal with speckle?
Excuse me,
every
sir.
other noise. Yes.
Hello.
Yes.
Someone are talking. Please suggest them to keep their mic switch off.
Yeah, please close your mics. You're right. Actually, Sishan, you have to, yeah, right. Okay. You have to close them. It's not easy here, because sometimes these mics go on, and I'm not judging. Okay, I remember also sometimes for me the mic goes on when I watched another presentation, so that can happen. Okay, try to figure that out. Okay, try to watch it a bit. It can happen. All right.
Still
Okay.
some people are talking.
Yes, also now including you. Okay, I'm continuing and trying to talk about a speckle. So what we do with noise is, when we want to get rid of it, is always at the end a statistical operation. So we are looking at the statistics and the statistical forms of speckle, and for example, the magnitude of the speckle has the distribution, or has a Rayleigh distribution, and if we know that, if we know which type of distribution it has, we can use that information to better remove it, for example, by using the gamma function in a speckle filter. Right? But what we do to reduce speckle is using statistics, some kind of statistics operation. In its simplest form, right, it's a mean. We could average. Okay, we take several pixels and we average of them. It's the simplest form of statistics. Okay. What it means for you is, if we say statistics, it means you can't look at only one pixel. You have to look at several pixels. Okay, you have to look at a number of pixels, and then you can start to form a mean filter. Okay, you can start to form a gamma function, right? But you need to look at several pixels, not only at one pixel. And to deal with Speckle is to look at several pixels to average, okay? In its simplest form, to use such a box window, okay, 5x5 window or something, and average all pixels inside of that. That would be its simplest form, okay? And in that case, you can reduce the effect of Speckle. Right, there are different ways to do it. You see the original SAR image on the left side is noisy and suffers from Speckle. On the right side is a Speckle filtered image here using based on Bayesian algorithm, Bayesian statistics. You see it's already very clear improvement, right, of the quality and interpretability of that. Another way to do it is to use temporal multilooking, so to average in time, right? If we have here several images and we overlay them, we put them one on top of the other, we can then average each pixel in time, okay? So if we have 50 images, okay, and we stack them one over another, and then we can average each pixel through these different images. And that gives you very nice results. Here you can get then also, you can keep high spatial resolution in that case and get very nice results under the assumption that nothing does change during your time, right? Otherwise you average different things. Before, many years, now it's many years before, this was a very theoretical slide. Okay, this is a very theoretical slide because you would need many images, right? You tell you to use 50 images or 100 images. People would tell you, you know, basically they would tell you to go away, right? It's I don't have so many images. It's too expensive. We cannot do that, right? It's a stupid idea. But nowadays we have so many images, right? Even for free, if you go now with, for example, the Sentinel data set, almost anywhere on the earth now you can download. Over time, there should be in the archive normally more than 100 images everywhere. So you could download them for free, okay, and average in time already. So this is what was kind of just a theoretical idea at the time of the ERS sensor here, as shown here, is now actually you can do that practically very easily now, okay? So averaging in time is certainly now a useful tool to deal with Speckle. Another slide showing you clouds and rain. I like to show these slides because your normal textbook is always telling you that SAR is like independent of the weather and not affected by rain, which is typically true, right? But not in all cases, okay? Not in all cases. So if you have very strong rainfall, like here, that's in Brazil, so you have a tropical rain here, and you have a short wavelength like X-band that is reacting with the water, okay? We mentioned that before. Water is a very good conductor. SAR reacts very strong with water. If there's strong rainfall with very large raindrops, okay, very dense tropical rainfall, okay, the signal is going to get reflected from that water, right? That's what you see here. The signal is reflected from the rainfall, from the what is the white areas, and behind that you see the shadow. The signal did not go through the rain. That can happen. It's not very often, okay? And your typical normal rainfall, your signal goes through that. But if you have very strong rain, tropical rainstorm, something like that, hurricane, you know, really strong rain, that may get reflected, especially in X-band, in this short 3 centimeter. To understand that, keep in mind the weather radar, the rain radar, the Meteorological Institute, sorry, are using, right? They use X-band. They use 3 centimeters to detect rain. So it's clearly affecting you, okay? You see that much less in C-band with 5 centimeters. This is already much less, occurs much less often. And in L-band, yeah, I never saw a rain in L-band image, okay? So, however, keep in mind, right, what the textbook says is not always true. You can see in shorter wavelengths very strong rain events. Penetration, right? This is an important point. So yes, your signal can penetrate. So if you have a short range, a short wavelengths signal, like here the X-band here, you enter the canopy a couple of centimeters. Okay. With C-band, you go much deeper. And with L or P band, you can reach down to the ground. Okay. Now, this is very important for you to know and understand. Right? Why is that important? Because we will talk about creating DMs and measuring motion, but when we talk about you create a DM and you create a DM from an X-band signal, your signal is, when you talk on forest, it's actually not the top of the forest, right? It is somewhere in the beginning of the forest and a couple of centimeters below it. With C-band, you're more deep in it, you're somewhere in the canopy. And with L-band, you are probably on the ground. So DM that you measure is probably on the ground. I said probably because it also depends on how dense the forest is. Okay. So how much you can penetrate depends on the wavelengths and clearly also on the density of the forest. Okay. If it's winter time and your leaves are gone, okay, you can even reach with X-band down to the ground if there's no leaves or very few leaves left. Okay. And if you have a tropical, very deep and high tropical rainforest, even in L-band, you're probably not reaching the ground. So it is clearly influencing from different factors. In dry soil, you see, the keyword here is anyway dry. If the soil is wet, you will be reflected more or less on the top because you react with the water. In dry soil, with X-band, you can get, I don't know how deep, a couple of centimeters, C-band a bit more, L-band. In very dry sand, it's even a couple of meters. Okay. And then in glacier ice, you can get actually rather deep, especially also in L-band, that is a couple of even tens of meters in ice, right? Frozen water, as long as it is wet, right? Wet snow, right, is different from frozen ice. So that makes it also, if we talk about, for example, if we talk about DM generation on glaciers and comparing different DMs that you generated over time, you have to keep in mind that where your DM is also depends on your wavelengths and on the wetness of your ice, because you're going to get then reflected somewhere on it. So it's sometimes then not so easy. So the penetration capability of microwaves can be very interesting for long wavelengths. You can penetrate some foliage, some coverage, but it can also make things quite complicated. If you think about now, where is actually our reflection coming from in detail, that can be quite difficult to answer. Okay. All right, but keep in mind that the penetration capability for especially soil on your normal ground is very, very limited. Okay, and as soon as there is some humidity there, not very dry soil, you basically cannot enter that. And you're definitely not going to go very deep under normal circumstances. right? Scattering, and also depends on how deep you go, which wavelengths you have. Are you getting directly scattered from the top? Do you have some multi-bounces, some volume scattering inside the canopy? Do you have a direct reflection from the ground, or a kind of double bounce from ground to the trunk of the tree and then back? Do you have attenuation? Do you go through the canopy and then get reflected on the ground? That depends on many factors, wavelengths being a very important one, but also the structure of the tree and the vegetation you're dealing with. Right? Do you have very dense tropical vegetation, or a European forest in winter where all the leaves are gone? Right? It's very, very different then. Right. That is also a funny slide I did long time ago. I should do it again, because at the time there weren't so many images. They were just at the starting of Sentinel. And I want to show you a bit the coverage, because we talk about the penetration capability of SAR, and that SAR can be used under almost all weather condition. And that is nice to know, but what does it mean? It also means that you get a very continuous coverage of an area. So I use that here over some time frame. Don't nail me down on that. Probably some months or something. I should do that experiment again. Anyway, at the same time, over the area, we saw like 9 Sentinel-2, so 9 optical images with a cloud coverage of less than 10%, while we got about 100 SAR images at the same time, right? So the clouds, depending where you are, if you go even more south, if you go to the tropics, it can be much worse, right? If you are interested in cloud-free images, and actually 10% cloud coverage is still quite a lot for some applications, you may need to wait several times to get your image, while within a SAR image, you can build stacks over a long time with very regular acquisitions. This can be very interesting. Also, for example, if you're interested in change detection, clearly, but also if you're interested in classification and you want to go and think about, well, I can use that to classify in time, to use temporal information for my classification approach, because you get these stable acquisitions. That's very, very useful for many applications. Right? So this all-weather capability is not only interesting for security and military, so they can look through the clouds at all time. It can also be interesting for other applications, because you get such a continuous acquisition, right? And now with the availability of Sentinel-1 data, you can also get that, right? Yeah, for free, and not so you can really make use of that. If you have to pay for every image, you probably do not want 100 images. Okay, it's probably something, yeah, it's nice, but I can't afford it. But now that the data is available, I can only encourage you to think about what could you do with that, right? What would, well, I'm not really a big classification expert, but for all of you who are into deep learning and thinking about how can we do that, it's also an interesting field to think about. What can I do if I have 100 images over time, right? Anyway, that was just on the coverage of images. Okay. We have to talk about the phase, and we will talk about that much more when we talk on interferometry. But let's talk a bit now about it, the phase of a SAR image. So we talk on the amplitude, on the pixel of the SAR image, the pixel strengths, but we also have this phase information. And the phase information is at the very end an information of the distance, right? So the phase is at the end the difference between the reflected signal and the reference signal that we build. And the very important information is the phase is cyclic, right? we go from here right back to here. We typically visualize it with such a color wheel, okay, from 0 to pi and then back to 0, right? Because it's then ambiguous. Okay, and that's typically the way we visualize that. Very colorful, nice pictures. Okay, but it's such a color wheel. And the phase is also when we sum up the different contribution of all this contribution in the inside a scatterer plays then a role if they are summing up positively or negatively. So it's a very important property of a SAR image, and we will talk about that a lot in interferometry, where we basically only look at the phase at the end. But now we are still looking at the amplitude, right? And so if we have such an image here, I'll make you a small example here, right? So we have corner reflectors, right, along the signal, okay, and we set them in half of the wavelengths, half of the band number here. So we set them up here so that they are lining up with exactly half of the wave there here, actually quarter of the wave. What we get then here is this return, okay? You can see it very clearly here. We see nothing, okay? What we get back is actually a black signal, an empty signal. We should see these corner reflectors, but because they're exactly positioned, they're perfectly positioned so they cancel each other out. So this one, let's say, let me give you a pen. I try to explain that a bit. Where is pen? Draw is fine. Okay, so I'm not gonna draw very ugly, but it doesn't matter. Okay, so and if that's our face, right, that one is put up here, let's say on top of that face. Okay, that one is half behind, so he's down here. Okay, so this one plus this one, and this one is plus, this one is minus. So if I add these two up, it ends up in 0. Okay, so they all added up down to 0 because they cancel each other out. Okay, this is the coherent signal. They have amplitude and phase, and if I add them up and the phase are negative to each other, they cancel each other out, and you get 0 signal back, as shown not very convincingly here. Not very convincingly because there could also be nothing there. Okay, I don't even know where it was. Probably in reality it was also here what I set up, or here. I don't know exactly where it was because I can't see it. Okay, but we set that thing up. You have to believe me or don't, right? But we did it. Okay, and actually you don't see that, and this is also some form of stealth technique. Actually, if you go and learn about stealth, they also use k-half for certain wavelengths of materials, so their reflections then actually cancel each other out. That is one point of nanostructure material that they're trying to use on that technique, right? So this may not really convince you. Okay, I get it, right? As something which you don't see is not very convincing. I did another stupid experiment on that. Okay, so I built another corner reflector, and I decided, because I'm very cheap, I want to save money. I thought it's a very good idea to build a corner reflector made out of wood here. Okay, so let's see. These are here. The ones you see, these points, these are traditional corner reflectors made out of metal, and our wooden corner reflector is here. You don't see it. It doesn't work. And actually, right, I was surprised. I thought you see something, to be very honest. I thought you're gonna see at least something. There's gonna be some reflection. But actually there's not. So we set up another experiment. And that time, actually, we saw it. This time we put it up here. This is the wooden corner vector. What's the difference between these two experiments? These things, they are pretty much the same. The difference is seen here, right? That's some water, okay, where you can spray some water. And before the satellite came, I sprayed some water on top of it. Okay, I made sure that the wood, and you can see the bit on the picture, that wood is now wet. It's not dry anymore. I put some water on top of it, and now we see it. Okay, so actually, that wood where is no water inside, you cannot see. Right? Honestly, I didn't know that when I made the experiment. You know, sometimes I'm also stupid. Okay, so then I use my stupidity to teach you. That's also something useful. I thought we can see that. I was thinking that because we can see tree trunks and we can see the forest. Okay, so, you know, we can see wood, right? But actually what we see is not the wood itself, it's the water in a living tree. A living tree has water inside. The dead wood here, we cannot see. It's dead, there is no water. If I add a little bit water on it, it comes up, right? It's the water that's actually reflecting. It's not the wood. And so that's also, for me, a very interesting experiment to do and to learn. And I hope also for you to see a bit that it's the water that plays a big role in it. Okay. Okay, let's talk a bit about polarization. I showed that slide already. I like that slide, but I show you too often. Okay, we have VV-HH polarization. All right. But in reality, it's a bit more complex. So we have a polarization moving around in an ellipse, again, elliptical form along the direction of our signal, right? In SAR polarimetry, the goal is to really analyze that. And I use here then the Sinclair matrix down here, where they're going to see, let me paint you that one again. They use a bit different letters here. They use here XX and YY instead of, could be HH and VV. Okay, before we used HHVV, sometimes in polarimetry, they write an XX and YY. It's the same thing, okay. And then XY and YX for HV and VH, okay. And you put them then into such a matrix to gather all for polarization. That's the so-called Sinclair matrix. And then this is used to analyze that. Right. Also, you see that small difference here. Yes, both is XY. If you have a monostatic SAR sensor, and typically you have that, that's normally what you have. In theory, theoretically spoken, HV and VH are identical. Okay, so it's quite common to set them here identically, right? So this is HH, VV, and this is HV, right? And then the total scattered power is here. Right, you can give it the square of HH 2 times the square of the cross polar, and then the square of VV. Right. And a simple way to visualize that, there are many ways, and I'm not really going into that, but there are many ways to deal and process and manage and visualize the polarimetry in a way that you can understand it or classify it, right? One way is to visualize it that you understand it, and one way is to process it that a computer better understands it, right? That's not always the same. A good way of visualizing it is the Pauli vector, the Pauli scattering vector, which at the end is, you see, HA. So you make that 3 bands, okay, red, green, and blue. Okay, so you can visualize it on a computer screen. Okay, and one band is then, and the one is then HH plus VV. Okay, one is then HH minus VV, and the last one is the VH or HV. And then you have such a scattering vector, and typically what we do with it, we make one, the red channel, green channel, and blue channel. Okay, and then we can visualize it on a computer screen. Right, and it's good because it's, I show you the next slide. It's very good. It's very close to the physical properties of the scatterer, and also easy to put on your computer screen and easy to process. And we can then physically interpret the meaning, right? Because they have then typically they represent 3 different scattering factors. One is the single bound scattering, that is then the HH plus VV, okay, that is then very strong for single bound scatterers where you just have scattering from the surface. While then HH minus VV is typically very strong for double bound scattering. So you see they're very good. The double bounds will be more strong if you do that, so that will come out, so you can separate the different bouncing and the physical, what's happened with the signal on the way. And the cross polar is very strong for volume scattering. Cross polar is if you transmit a horizontal signal and you receive a vertical signal, or right, you transmit a vertical signal and you receive a horizontal signal. That anyway, in both of the ways, that means something changed the signal on the way. Okay, if you transmit horizontal and you receive vertical, that signal has changed on the way in its scattering. And that here happens, for example, in volume scattering. You remember I showed you that slide. Your signal goes into the volume, it gets reflected inside and get reflected again and get reflected again. And each time it can be, maybe it's a little bit shifted. The wave is a bit tilted. So if your wave hits something which is not, perpendicular, actually the polarization also gets turned a bit. Okay, if that happens very often, horizontal signal can turn into a vertical signal. Horizontal polarization can be changed into a vertical polarization, right? And so that happens more commonly in volume scattering. And so that is an indication then that you have volume scattering, right? Can also happen for other reasons, right? Nothing is perfect, but it's one way, right? Let's take a look at an example that is, I think it's San Francisco. I did not write it here. Anyway, okay, that is here it's some L-band data. You see, it's quite an old example. That's the amplitude image, and if we change it to in that Pauli scattering matrix, you see, we can now have a form of classification already. Okay, we have bluish is coming from the single bound scattering. You see that is coming from the water surface, and also a little bit in the other one. You see some bluish sometimes inside. The green, that is the HV and VH scattering, right? When the polarization has turned, that's typically for volume scattering. So it's an indication for vegetation. That's why you typically make it a green color, okay? Because we like to see vegetation as green, okay? It makes us more easy to understand. And you see, it gets the vegetation already with this very simple method rather well. And then the last one, the red one, is the double bound scattering, and you see that then gets more common in the urban areas where we see some double bouncing where this is actually happening. So it's a simple way to visualize polarized SAR data, and it's already giving you a first type of classification, right? And a direct way to interpret the bounds of the signal. Right? The Pauli vector is only one way. It's a rather simple and I may say older way to do that. Okay, but there are many other ways which I'm not showing you here. I can only refer you to literature on that one or another course, because it's also a very, very deep and interesting research field, and we can't do all here. But the Pauli would be a good starting point to do that, right? And then we can also do classification with polarimetric data, and we can use the typical classification methods, right? K-means, maximum likelihood, whatever you want. But typically we are based that on not on the, we don't put the pure data inside. We base it on some kind of decomposition like the Pauli vector. But for classification, we rather, it's, I think, common to use the Claude or there's so many, you see, H alpha, A Wishart, Freeman Wishart, the different types of decomposition that work very well with classification. Pauli is good for visualization, but for classification, these ones are a bit better. And then you can use the decomposition and put it in your classification method. As we had the question on software, right? The ones of you who are interested in polarization or want to learn about polarization, there's actually a great free tool available for polarization that is from the ESA, from the European Space Agency, PolSAR Pro, and you can download it for free. And it has lots of this decomposition inside and tutorials on polarization. And I think some of my slides are even from that tutorial. So that's a very good tool, because we had one question on software. If you're interested in polarization, that would be the best tool even available. It's even better than commercial tools for that one. That one is for polarization, really, really good tool. PolSAR Pro, we can also put it in the chat later. I can sometimes show you a link on that if you're interested. And that can then be used for decomposition, and then you can put the decomposed data in the classifier that you want. All right. However, right, we are having Speckle, we're having the Speckle effect in it, also for sure in polarized data. So we have to deal with that. Okay, and one way to deal with it is averaging the data, and it is then recommended to use some kind of region-based classification. So do not use pixel by pixel classification, but instead try to segment the area in regions and then classify these regions, use then statistics on these regions to remove the Speckle effect and then classify based on that. Going to get much better results, because the Speckle effect is really messing up your classification. Okay, if you do not deal with it, it's actually rather meaningless if you do it pixel by pixel. So region-based classification and the kind of decomposition of the polarization is typically the way to go. All right. Okay. Let me look at the time. Wow. Okay. I showed that slide many times. Okay. I show it again just to ease you into it. We are now talking a bit on SAR image interpretation, right? And on some examples. And I like the example of bridges, because they have these, we can see these different bouncing very clearly. So we have the single bounce effect, right? That is, we are, for example, you're hitting that bridge and then directly reflecting back to the sensor. We have the double bounce, for example, we hit the water, right? We get reflected from the water, hit the bridge, and then go back to the sensor. Or similar. We hit first this bridge, get reflected to the water, going back to the sensor. There will be the same traveling time, so they come back at the same time. For bridges underwater, we often also find a triple bounce. So we hit the water, we hit somewhere under the bridge, that signal gets reflected back to the water and then back to the sensor. So 3 times bouncing, right? So this is the signals that we see, and all of these signals, they have different running time, okay? So the single bounce would be the fastest, right? Because it goes there and back. If you just measure distances, it's the shortest. The double bounce, right? It goes there, there, there. It's a little bit longer. And the triple bounce for sure is even more long, right? The distance is even more long. The double bounce has one effect. The double bounce from the timing is always the same as the single bounce at exactly this position, right? Exactly, you can say the nadir position of the bridge. So if you can paint it on a piece of paper if you don't believe me, right? And measure it, right? The double bounce from here to here to here is always the same distance like the single bounce here, which is to say the double bounce at the end will be at the precise position of the bridge, and you can always use that to identify the true position of the bridge or a building if you want to. Okay, let's take a look. Those of you who are not from Wuhan, I show you some bridges that we will talk about. So this is, I don't even know the real name of the bridge. That's the bridge from Hanyang to Hankou. So let's call it Hanyang Bridge. Okay, you see that has here such an arc here. Wait, you didn't see my mouse. I think you don't see my mouse. So this one here that has this arc here, right? And this one is the large bridge here. This one is the so-called first bridge or the big bridge in Wuhan, which has here these, I think, 7 structures here. It's also a 2-level bridge. The first floor is a railway, and the top floor is the cars. The cars are on top floor, and here under, here are the cars, and here underward there is the railway going through. I mentioned that because you're going to see that in the radar image as well. And that building here, that is the that's the Mingsheng Bank building. We will see that same image. Okay, that was several years before. That was the highest image, the highest building in Wuhan. Okay, I will show you that, just that you have, you can try to remember these pictures when we go through the SAR images. Maybe helps you understand. Okay, this is that Hanyang Bridge here. You see here that, you see that arc here, right, in single bounce. Okay, this is the arc of the bridge, the red arc that we just saw in the picture, and that would be here the single bounce of the road structure here. Okay, so this is the single bounces hitting the bridge and directly go back. Here we are seeing the double bounce, the very strong signal here, right? This is the double bounce. So this is the signal hitting the water, getting reflected from the water, hitting the bridge, and then going back to the sensor. And at the same time, signal hitting the bridge, hitting the water, going back to the sensors. The distance is identical. So both come back at the same time, also helping to get that signal very bright. The double bounce will typically be a very bright signal. And behind the bridge, we also see the triple bounce. Here, this is signal hitting the water, then hitting the bridge, getting reflected back to the water and back to the sensor. So we have 3 bounces here, 3 reflections. That path is longer, so it is more far away from the sensor. It's imaged behind the sensor. Okay, so these are a typical structure of bridges with the 3 bounces, and you see them very commonly in SAR images. This here is similarly, this is the image of the first bridge, of the big bridge in Wuhan. Right, we see here the single bounce. You see this line here is the single bounce of the road on top of that bridge. It's a 2-level bridge. This one here, the second signal is the railway, right? The single bounce of the railway of the lower level. Then we have the double bounce, right, of the way, and especially the double bounce of these poles here that are holding the bridge. You see, they are very strong. And then behind the bridge, we see here rather chaotically the triple bounce of it. Now, we are not very sure in all details on why it is a little bit more chaotically. There are two series, probably both are true at the same time. Okay, one is that the water wasn't that calm, and it is more, we had some waves on it that made the triple bounce more shaky. The other series, that because it is we have 2 levels of the bridge, the signal goes also inside, and we have reflections between the railroad, the rail layer, and the road. And we have then probably different reflections. That might also be the case, right? Okay. So we went a bit into interpretation. Let me see. Okay, I go a bit, start a bit on the interpretation. We're not gonna finish that today. And this year, okay, let me paint it. It's helpful if I paint a bit this building here, right? This is this high Minsheng Bank building in Wuhan, right? And you see here the huge layover of that building here, laying over here in that direction. Okay, the double bounce is somewhere here, I assume, and this is the layover of that building. Okay, all right. Now that is the ascending orbit here. Now let's take a look of that building from the other orbit. Now from the other orbit, it looks like this. Okay, and what we see here is well, a layover and a very, very, very strong scattering center. So this here, what you see here, what I paint here on the side, these are side lobes. Okay, these are the side lobes I mentioned, which can appear when you have a very, very strong signal, very, very strong reflection. That reflection is very, very strong, extremely strong. Actually, these side lobes here, you can see over the whole image. Okay, they will go on and on up in all 4 directions, come over the whole image. Very, very strong reflection. Because what's happening here is that we here directly hit that building. You see, there's a small lake here in front of the building. So the signal comes, hits the lake, hits the building, and the building is directly perpendicular to our looking direction. And it's a very high building. So we get a very, very strong signal. And yeah, actually, I just show you that more or less for fun. Okay, from the backscattering strength, we can, as we discussed it on Friday, to detect the ship sizes, right? We can also estimate building heights. In this case, it's a function of the area of the building, right? And right, this one here, right, that angle here, that is the direction of the building with respect to your looking angle, okay? And in this case, we are really at perpendicular at it. So we get here very high reflection back, basically a mirror reflection back. And we could then, if we know something about the material of the building, from our reflection strength here, we could calculate the area that we see, and we could go to for the building height. In practice, it doesn't really work because you don't really know much about the material and many other variables you're not really knowing. But in theory, you can do that. Important is here the reflection is so strong, because we have a really huge building area that we see, and we directly hit it at 90 degrees. So we get a very strong reflection here. Right, this reflection is extremely, extremely strong. Okay. SAR artifacts and ghosts. Let me check. All right, maybe we take a break here and take a look at the questions that you have. Sishan, did you prepare some of the questions?
Yes, Professor. I have prepared questions, so can I
share there many
my
questions? Let me ask, are there many questions?
Yeah, approximately 40 questions.
Okay, let me do some questions now and probably more next time. 40 questions a lot. I'm very happy. I'm very happy if I get a lot of questions. That makes me extremely happy. But let's try to do some questions now, okay? Before we come into the next topic. I stop sharing.
Okay,
I stop sharing. I stop sharing. Okay.
So yeah, okay. We will move from first question. Can you see?
Not yet. Now it's coming. Now I can see. Okay.
Yes, we can see.
Okay.
Oh
no. Is it
okay? Is it clear now?
Yeah, but it started at question 9. Is that correct?
No, question 1 is not there.
Yeah, I see number 9. Yeah, no. Okay. Maybe it's a bit delayed. Okay.
Oh, okay.
Okay. Yeah, now I can see. All right, question 1. How do we differentiate if the vertical signal returned to sensor is a vertical signal sent from the radar or a horizontal signal that has been modified into vertical? So if it's VH or VV. But right, so it's actually, we know that, right? We know that because we are sending out the signal we are transmitting. We know what we are transmitting because we create our own signal. So we know if we transmit vertically or horizontally. And similar, we know what we receive because we also have a filter in front of that, and we only receive horizontal or vertical. So we know if it is VH or VV. Actually, when you get the SAR image, it will be in the metadata, right? If you order a SAR image, sometimes you can even choose what you want, right? So we know that. However, what happens, why a signal is changed, okay, from, let's say, vertical to horizontal, we can only guess, right? Right. And typically it is volume scattering. It had many scattering, or it hits a tilted surface. If your signal hits a somehow tilted surface, right, in either right direction, it is also changing the polarization. So your polarization is rotating with that tilt. So that also can change in these polarizations. Okay. Could you please give some explanation about why VV is a preferential choice? I cannot, because I never ever said that it is a preferential choice. Okay, if there would be only one preferential polarization, we wouldn't do all of them. Okay, now VV is often a preferred choice because what you are, how to say, well, if you are transmitting a vertical signal, okay, it is reacting with objects that are also physically vertical. That's to say, you will have maybe better reaction from like things that are also vertical, like your grass or your fences or something like that. They may react more to that, which is often what you prefer. And sometimes they're also less affected from double bouncing. HH is often more affected from double bouncing, so some people do that. But it's not like a general rule that VV is always the best, right? That is not the case. Now, I guess some of you just did not understand what I was talking about. I give you another example. Okay, I give you an example on how they react of that. So if you think about, I don't have a slide who shows that. Anyway, let me just explain you. If you think about power lines, okay, you have these power lines, okay. If you send out a VV signal, a vertical signal, right, that signal will often not react with the power line because, you know, it goes vertical, that line is horizontal, it just basically goes over that line, does not really react with that. If you send a signal horizontal, it often really hits that power line and gets reflected, okay? So it is very common, for example, that you then, when you compare VV and HH, that you see the power lines, for example, in the HH image, but not in the VV image, okay? Because that line is horizontally oriented, okay? And the horizontal polarized wave, horizontally polarized wave, reacts more strong with horizontally oriented objects, okay? However, if an object is large enough, right, then it also hits that, okay? But sometimes these power lines, they are below the wavelengths of the signal, okay? I hope that power line example can help you a bit understand how is these differences and what can they react with. Okay, can phase ambiguity be a factor for change in the N value? Yes, I was hoping to show you that when I showed you some experiments that you put them up there. So the phases, they react, you have a coherent signal. So when you add up different phase contribution, it depends on the phase and the amplitude as well, and they can, for example, cancel each other out. So yes, that does influence the N value. It does influence. It's basically the root of the Speckle effect. Okay, question 4. In your experience, what types of polarization is suitable for the issue of monitoring land subsidence? Is VV plus VH good enough for monitoring land subsidence in a regional scale? Yes. Yes. Typically for land subsidence, in that case, we would typically prefer VV instead of VH. VH is reacting strongly with vegetation when we will come to that, but when we do interferometry, we do not like vegetation. So we do not like polarizations that react strongly with vegetation. So we would typically move toward VV. However, as in many cases, for special applications, it might be different. Is Sentinel-1 image sufficient to detect soil moisture? That depends what you mean with sufficient, right? We can detect differences in soil moisture with Sentinel-1, but is it sufficient? That depends what you want. How precisely do you want to detect it, and so on. For many soil moisture applications, they use passive microwave remote sensing data very commonly, I think, because it's a little bit more suitable if you are interested in soil moisture. Okay, there's difference between gamma O and sigma O and power and amplitude. Right, that's a good one. Right, power and amplitude. I'm actually not sure. Well, we typically have the difference between amplitude and magnitude. So amplitude would be the square of the magnitude in that case. Amplitude is the square root of the magnitude, and and magnitude is the square of the amplitude. And gamma O and sigma O, sigma naught, sorry, gamma naught and sigma naught. I'm hoping I'm not saying it the wrong way. Please check, double check it. So I think I hope I'm not confusing both of them. Okay, gamma naught. If I'm